Okay, I just wanted to do three presentations just quickly around radionuclide production and some of the facts and fantasy that exist today in various debates. Whether radionuclide production in a nuclear reactor, for example, is necessary. And so these are just three facts versus fantasy presentations to try to set the record straight on a few of those issues. The first thing to mention and get our heads around before we move on to radionuclide production in a research reactor is to recognise that radionuclide production in a research or medicine reactor is not the same as nuclear power. A nuclear power reactor is a different debate, it has different capability, it confronts different issues. They're two completely separate debates, and to be honest, is that any attempts to make the debate on a research reactor for medicines and nuclear power reactors the same debate is actually fairly irresponsible and poorly informed. So it's important to realise that a nuclear reactor for research and medicines, the things that make it unique, so the favourable characteristics that make it ideal for radionuclide production are the same characteristics that make it a complete waste of time for a nuclear power station. So you're not going to have a nuclear reactor that is designed for medicine production all of a sudden be turned into a power reactor. So we're going to break the three presentations up into these three topics. The first area is the questions that have been raised across different political and social circles. That is a nuclear reactor inefficient and a high cost for radionuclide production? And if that's the case, why is the Australian model any different? Other questions include can't radionuclides be produced by alternative means like a cyclotron? And doesn't that make the reactor redundant? That'll be part 2 or part B. And do we really need nuclear medicine? So we'll talk about that in part C. So part A, there's discussion that nuclear reactors are inefficient and high cost. And the examples of that include the Canadian example where they invested $600 million to develop two new reactors. And they've essentially been mothballed because they didn't reach their production capacity and there was a few technical and regulatory issues. And so obviously we want to look at how the Australian model is different to that. So let's start with reactor efficiency. And when we actually think about how a reactor works, it's a pretty simple concept. The first concept is we actually have uranium-235. And when you actually pull uranium out of the ground, is that very small, less than 1% of it is actually uranium-235. So we typically have to enrich it. So most of it's uranium-238, which is not particularly useful in terms of a standard uranium fission reaction. There's other uses of uranium-238. But if the majority of it's uranium-238, and we need to get uranium-235 up to around about, so for the Australian reactor, 19%, or just a fraction short of 20%, and that's considered low enriched, then it means that you've got to remove a lot of the uranium-238, which then becomes waste. We call that depleted uranium. So we have our uranium-235, we put it in an environment where there's neutrons floating around, which is in the center of the reactor. A neutron, interacts with uranium-235, and these are called thermalized or slowed neutrons, so we slow them down to increase the chance of that reaction. And it creates uranium-236, which is highly unstable and virtually instantaneously undergoes fission, and in that fission process it creates energy. It gives off gamma emissions and other things, gives off 3 more neutrons, and it splits the mass of this into 2 products. It's unusual for it to be a split in half. It's usually one larger product, in this case 1,3,4-tin, and a smaller product, in this case molybdenum-99. And so that's what occurs in a reactor. And so we get a whole bunch of fission byproducts. And the one that we're most interested in is molybdenum-99 because it's the parent product of technetium, so it will go on with a 67-hour half-life and decay to technetium-99m, which is what we use in nuclear medicine. So this is what we want to pull out of the system. You can see it's self-sustaining, so it produces 3 new neutrons, and each of those can interact with another uranium-235 to produce another fission reaction and 3 more neutrons. And so part of the process is to actually control that reaction by absorbing some of these neutrons with control rods, so it doesn't get out of control. So we want to absorb those, so we typically have some neutrons that we take away to do research in the neutron room, and then others that move on to create additional fission reactions. So when we talk about reactor efficiency, we're talking about the cost of its production. So we talked about the production of that molybdenum-99 and how much that costs to produce. And so we actually have to have the reactor itself, which is a large investment, $400 million or something. It's got the manpower associated with that, maintenance, the product to put in there. So we actually have the targets as well as the fuel. So the fuel is low enriched uranium. And so it actually has reduced, waste because it's a lower enrichment. But our target's also low enriched uranium. It's the only reactor in the world, in Australia, where you actually have low enriched targets as well as low enriched fuels. But we have to actually have that target irradiated. We have to extract it, the molybdenum from it, and then turn it into the generators and ship it to departments. So there's these typical processes that need to occur. So we actually have the production that occurs in the reactor. Then we actually have our target that has been irradiated and produces our molybdenum and a bunch of other byproducts. So we have to separate our molybdenum from all the other things that have been produced. And then when we have our molybdenum, we need to turn that into a generator, which is then shipped out to all the hospitals and clinical departments. And now the reason that some people might consider this inefficient is simply because of this time. These reactors are dedicated reactors for radionuclide production, so they don't do anything else. And this is typical in the Canadian model as well as the European models. And then what happens is that once the reaction has been done, the fission products are actually bundled up, put on a truck, and shipped. In Europe, this could be across a country's border. In Canada, it could be 100 or more kilometres. So it's shipped across to a separate plant. And once you're in that plant, then they do the molybdenum extraction. And when they do the molybdenum extraction, they then repackage it and ship it by truck. Again, it could be across a border if that was in Europe. It could be 100 or 200 kilometres if it's in Canada, to another facility, a third facility, where they actually then turn that into a generator production, or generator for production of our technetium-99M. And when those generators are produced, it's then shipped out to our hospitals and clinical departments. So each time we actually ship it, and you've got increased cost of shipment, of handling, of packaging, of unpackaging at the other end. And importantly, even though the molybdenum has a long half-life of 67 hours, each time you ship it, you actually decrease the amount of activity that you've got. So what happens is each of these steps increases the cost, increases the time, and decreases the activity. So our cost and decreasing our activity further increases our cost. So the dollar per unit of molybdenum increases not only because you've got duplication of that process, but also because you've got radioactive decay. We get to the next system, increases the cost, increases the time, decreases the activity, and therefore increases the cost further. Okay, but what we end up with in the end is a generator where one reactor provides an entire national supply plus potentially international demand. So one reactor has been able to do all this even with these inefficiencies in there. So we end up with a dollar amount at the end that's been associated with the costs that have been accrued through this entire process. So ultimately is that it's actually a fairly efficient process, and the amount of molybdenum that we get is quite financially sustainable. But you can see that there's inefficiencies there and there are cost pressures there. And this has actually attracted some criticism. The Australian model is different, and the reason that we sort of ignore sometimes those criticisms of the cost and efficiency of radionuclide production in a reactor is because we've overcome most of those cost inefficiencies. And so this is the Australian model, and you'll see there's similarities. We still have those three processes that occur. The difference is this occurs in a centralized place. The reactor production, the molybdenum extraction, and the generator production all occur on site at ANSTO in Sydney. So it's all one site. There's no shipping, there's no lost time associated with that shipment, there's no extra costs associated with packaging, shipping, and unpackaging. It moves from one building to the next building to the next building and then is shipped out to the hospitals and clinical sites. So you end up with this massive efficiency that decreases the costs, increases the activity, which further decreases the cost. Okay, because you have more activity due to less decay, due to those time efficiencies that you've saved. So that's the first aspect that we've been able to actually show, that the Australian model is far more efficient than others. But we have these other concepts that occur here. So we just talked about that single site where you decrease costs, decrease time, increase activity. Increasing the activity also decreases the costs further. But Australia's reactor is the only reactor in the world that uses low enriched fuel and low enriched targets. And what that means is that we're actually got less waste, so we'll talk about waste at another time, but there's less waste coming out of the system because you've got a lower level of enrichment, which means that you've got lower uranium-238 waste. So that's the first thing. So that has some decreased costs and decreased waste, which decreasing the waste also decreases cost and storage. So that's one efficiency that comes into it. There's two other really important efficiencies. Number one is that a lot of the other reactors around the world are not research reactors. The reactor in Sydney, the Australian reactor, has a significant research component associated with the Bragg Institute and the neutron room, where some of the neutrons in the high flux neutron environment of the reactor are channeled through some ports into a separate neutron room, into some really high-tech research equipment that's used from everything from understanding disease to understanding the environment, environmental sustainability and protection, metallurgy. There's a whole raft of applications of that neutron room. It's a fantastic facility. I encourage you to look up the Bragg Institute and the neutron room and just have a look at some of the research that's being done there. But the reality is, though, is that when you create this high neutron flux associated with the reactor to produce this molybdenum, you've actually got this double purpose. This repurposing of the leftover neutrons, instead of them being wasted, is that you actually have some research outcomes that come from that. That's associated with some research grant income and obviously the benefits of improving the understanding that humans have of health, disease, the environment and science. So it means that we have less waste and better outcomes. But there's also a commercial arm to it, is that the ANSTO reactor is probably the best facility in the world for irradiating silicon, for example. So we actually irradiate silicon from around the globe here in Australia. And what that does is actually creates a commercial aspect of the reactor, which further decreases costs, because the income that comes from the commercial aspect can offset the maintenance cost. It can offset the initial establishment in infrastructure costs. It can offset some of the personnel costs. So it's a significant benefit to have that extra arm that underwrites some of the costs and the productivity. So what it ends up being is that the Australian model is superior to those around the world and unique compared to those around the world because it provides this economic and environmentally sustainable model that's cost efficient, it's cost effective, produces high quality product, and ultimately it enhances the health and well-being of all Australians. So I've mentioned generators, and I only say that we're only going to cover generators briefly because we've used those terms and just so you understand how it works, is that we don't directly produce the technetium-99m in a reactor. We could, and it could be a byproduct, but what we'd rather do is produce its parent, molybdenum-99. So technetium-99m has a 6-hour half-life. That doesn't give you a very big window of opportunity to do things like quality control and shipping things out. So its parent has a longer half-life of 67 hours, and it decays to technetium-99m. So if we deal with the molybdenum-99, and we can load that into what's called a generator, which is just a small aluminium column, it's like a little crucible, that the molybdenum is attracted to the aluminium, is bound there. So as the parent decays and becomes technetium, we can actually run saline across that and remove the technetium, leaving the molybdenum there, and we can use that on a daily basis. Okay, so typically we elute the generator, and that's what it's called when you remove the technetium. It's a very simple process. Typically we do it once a day, but you could do it 2 times a day. So it's actually designed so that you actually end up with around about 4 half-lives of the daughter. You end up with equilibrium, which is going to be 4 times 6 is 24 hours, so about once a day. But because of the way that the decay of the parent works, the maximum amount of technetium occurs at around about 18 hours. So it means that if you eluted this at 8 o'clock this morning, then we could actually potentially elute it again in 6 hours time after 8 o'clock, and there would still be 18 hours from that second elution before you elute it again the next morning at 8 o'clock. So that second growth time is about 18 hours. So you could potentially increase the amount of technetium that you have access to on a daily basis by eluting twice a day. And so that's just an efficiency that we can build in. But what it means is that we've actually got a supply of technetium on hand all day, every day. It creates its own radiochemical purity through the elution process, so it's highly pure and it's pyrogen free. And typically one generator supplies 1 week of product to a department. You don't need daily shipments. It's 1 shipment per week. And in fact, you might find that we create an additional efficiency, because you might have a company that owns 2 or more departments, where one is big and busy and the other one is small. And so the old generator from the big site in week 1 can be shipped to the second site in week 2, the smaller site in week 2. So there's a number of ways that we create efficiencies in the amount of technetium that we need to use. And I only point that out because when we talk about cyclotron production in Part B, all of this is lost. So it's a simple system. These are about 22 kilograms. Most of it, the weight comes in its lead shielding. We have a small glass vial that has aluminium in it. It's a little bit more complex than that, but the molybdenum is tightly bound to the aluminium. As it decays to technetium, it's more loosely bound. So if we run saline across that column and up into an evacuated vial, then it actually washes off the loosely bound technetium and leaves behind the tightly bound molybdenum, and so we end up with our technetium, and we can do that once or twice a day. And so this is just the elution profile I mentioned before, where this red line is the decay of the parent. So you end up with on Monday a very large amount of activity, and on Friday a smaller amount. And so we typically work out our schedules so that we have enough on Fridays, and Mondays and Tuesdays might be busier days. But it allows us to actually elute at a time when you've got a maximum amount of activity or equilibrium, and then it grows back again, and then you elute and it grows back again. So you can see that the growth back of the technetium that's available on the column is much more rapid in the early few hours after an elution. And so that means that you could re-elute several times and without having a significant detriment. So you want to increase the amount of technetium that's available in your department. And the other thing to consider is that we focus on technetium, and the discussion around cyclotron production of technetium 99M is important. But what it actually ignores is that reactors don't just produce technetium. Technetium, 70 to 75% of nuclear medicine studies that are done. But there's a whole raft of other radionuclides that are produced in a reactor, including some really important therapeutic radionuclides. In Australia, probably the 2 most important ones that we produce are lutetium-177 and samarium-153. And these are produced from neutron activation in the high flux of the reactor core. We can produce P32 and strontium-89 and iodine-125 and chromium-151 and a whole raft of others. But these are the 2 most important ones in Australia from a therapeutic perspective. So this is important because if the reactor's not there, even if we could produce technetium-99M in a cyclotron, which, as you'll see in Part B, is inefficient and high cost, so it's not really going to provide that solution, is that you're ignoring the fact that we have these other really important products that we can't produce in cyclotrons, and so we still need a reactor for. So reactors are for medical radionuclides that are diagnostic and therapeutic in nature. And just schematically how neutron activation works is that rather than it actually being a fission reaction, so these are the fuel rods, you could actually put a target in here of uranium that's going to be undergo fission in this neutron flux that produces our molybdenum-99. But you could also put in other targets that are not uranium-based targets. So you can put those targets into the high neutron flux, and those targets might be something like P31 in this example. So if you put this P31 target in there, these neutrons bombard it. Again, they're thermalized or slowed neutrons, and it creates a reaction that produces P32, and the excess energy is given off as a gamma. Okay, so you end up with P32, which you could use for therapy. So that's an important application that occurs in a reactor. It's not just fission products, it's also neutron activation. So the last bit is, what about the waste? And I just wanted to put the waste into context. There is waste. There's waste associated with cyclotron production. There's waste associated with a whole raft of things. Just cooking, eating, production of fuel. All those things have waste. When we talk about the waste for radiation in Australia, there's what we call legacy waste, and the legacy waste is all the waste that we've accrued in the past. And a lot of that waste was accrued at times when we didn't really understand radiation safety as well as we did. And there was, to be fair, there was probably some irresponsible use that probably could have been avoided, and we certainly wouldn't do today. And so that produces large amounts of waste that today would be much smaller volumes. So some of that was from ANSTO, but some of it that I'm referring to is CSIRO, some experiments that were done where we have barrels of radioactive soil, for example, that are being stored, is that you would just think about doing those differently today, so you weren't worried about, or you didn't have to consider the sheer volume of waste that we have to store and dispose of. So if we talk about that legacy waste, and it's important because the waste that we produce moving forward is a different level of waste. It's a different, because we're far more responsible in the way that we produce it, the way we manage it, the way we reduce its volume, and then of course the way that we store it. So when we talk about the legacy waste, is that if we really looked at how much legacy waste there is, people think there's a huge volume of this legacy waste. It's around about 0.2 millimeters cubed per Australian, and that's per Australian that's currently alive. Okay, so a family of 5 people. So if you had a family of 5, each of those family of 5 would be responsible for storing 1 millimeter cubed of waste, and that includes all low and intermediate level waste. Australia doesn't have high level waste. So that's smaller than the ball in a ballpoint pen. That's the level of waste that we're talking from all of the legacy waste that's out there. In the lifetime, assuming 80 years, it's 82 years, but we'll assume it's 80 years of an Australian, their share of the ongoing waste, so we're talking about the future production, sorry about the spelling mistake, talking about the future production, is 0.139 millimeters cubed over their entire lifetime. Not 1 year, 0.13 millimeters cubed over their entire lifetime, 80 years. So it's a very, very small amount of waste that we're talking about. It doesn't come close to any other production facility in Australia, whether it's fuels or even producing soft drinks. The amount of waste is much higher. So in summary, OPAL, which is the reactor at ANSTO, so Open Pool Australian Light Water Reactor. It's cheap, it's efficient, it offers very flexible service delivery and a world-leading capability. Australia leads the world in radionuclide production. Australia's facilities are the envy of the world. I go all over the world talking to different communities, and everyone envies the Australian facility, not just the Australian facility that we have, but the way we went about it. The foresight that both ANSTO and the Australian government had in producing a high-class research reactor that could produce nuclear medicines now and into the future, before the old reactor, the old HIFO reactor, was redundant. The health and well-being of every Australian is improved because of the research, the diagnostic and the therapeutic applications associated with the reactor. And none of those things could be lost.